So yeah, thank you, Leighton, for the invitation. So I'm going to try to give an introduction to a particular problem that is part of a bigger field of research, which is the out of equilibrium dynamics of many body systems. And okay, you will hear a lot about these problems during the conference. I'm going to focus on one particular realization, as I said, of these generic problematics, which has to do with the dynamics of closed classical systems of a very special kind, which is that they have the property of integrability. They are integrable. And I will explain everything I mean by all these keywords like many-body, classical, closed, and integrable during the talk. But let me give you a little bit of background on, which is the interest. No, no, this is behind. Okay, so it's fine. I think it's readable. I think it's readable. So let me tell you why people are getting interested in looking at closed system. What does closed mean? It means that there is no contact with any environment. I use it as a synonym of isolated. And so let's say no surroundings, no bath, no contact with anything else. So in the context of quantum problems, especially people who do atomic physics, they have been interested and have been realizing a lot of experiments recently on cold atoms that perhaps you've heard about. And those cold atoms are a certain number of atoms which are within the time scales of the experiments isolated from the environment. So the interest in looking at the dynamics of closed systems, or regain in interest in looking at the dynamics of closed systems, came from basically those experiments. I'm not going to deal with quantum mechanics in my talk. I'm going to deal with classical physics. I will define this, Newton dynamics, basically, because a lot of the special properties that these people are seeing in their experiments and in their calculations are not essentially quantum. They are essential to the fact that their systems are closed, and in some of the cases that they are integrable, and I will define this in a second. So closed is just isolation from the rest of the world. Many-body is that you have many degrees of freedom in interaction. They're not independent. They talk to each other. And this is what also makes the dynamics interesting. So the fact that they can have collective behavior and do something globally of interest and not just, independent individual particles following their own life. So integrable, I will define later on in the context of the model that I will consider, because it's a little bit more technical, and I need to introduce a certain number of quantities. Right? and there was light. Thank you. So, okay, this is the context of what we are going to do. And the other key word here is, of course, dynamics. This is evolution in time following certain forces that depend on the problem that you want to look at. I will define one. And out of equilibrium, you will see in a second. So which are the kind of questions that these quantum people have posed, and how can we, translate them in the classical realm? So classical physics, what am I going to have? classical mechanics, let's say, or classical dynamics. I'm going to have degrees of freedom. They could represent particles, so they could represent positions and momenta of particles, for example. And they will follow Newton dynamics. Okay, so just traditional classical mechanics. And the question that you certainly studied or at least mentioned in statistical physics is related to what happens if you have a large number of degrees of freedom. So there is n, the number of degrees of freedom, and in the limit of n going to infinity, statistical physics asks questions of the kind, okay, don't look at the evolution of these degrees of freedom one by one and solve the Newton equations for all of them and look at the time-dependent evolution, but you ask questions of ergodicity. Or in other terms, you use the ergodic assumption to make a jump, and instead of solving the time-dependent evolution of this problem, go to stat phys, which is our field of research, and compute averages with some prescription that don't involve time. So let me remind you, what is the ergodic hypothesis? Let's imagine that you have this system of n degrees of freedom and that you have some observable with nice properties like, some global observable of your system of n degrees of freedom. Like, for example, you could look at the kinetic energy, you can look at the potential energy of your problem, or you can do a measurement of some other sort of thing. But that is some global. I mean, it involves a lot of particles. It's not just that I'm looking at one part. And let me call it A. Okay, this is the observable. In the mechanical view of the problem, this A depends on the positions and the momenta of the particles that you have, and say that, okay, I'm in d dimensions, let's put arrows, and these mu's are the labels of the particles. Okay? So this, through the time dependence of the x's and the p's, is a function of time. Okay. Now, the step made by the ergodic hypothesis is such that in the limit of n large, you compute an average over time of this object. So say that you have time here. This is the initial time, time equals 0, let's call it, of your evolution. Here you chose initial conditions, and you evolve with the Newton dynamics. You let time advance, and then after this transient, you start measuring an average over time of this thing. So in other terms, you measure star. Let's call this time the star. So this is a time average of your observable A over a time window of length tau. So you start measuring, say, at some time t and t plus tau. You measure over this time window here. You normalize by the length of the time window, and you do it first in the limit of n going to infinity, and then long times. So long time window, long tau here. I put some time scale here. I don't know what it is. It's something sufficiently long, this tau, so that this averages. And this is after the transient. So this is the time of the transient. After which I'm going to start measuring. So in principle, this object here, which I'm going to call A with a bar over here, depends on time, no? In principle, depends on the time where you start averaging. Now, in practice, when this ergodicity holds, when this ergodic hypothesis holds, this average here should be equal to an average over some measure or distribution function of your positions and momenta of the particles, but where there is no time, right? This is the statistical physics average, well, that's a time-dependent average, right? So this is the starting point of your statistical physics lecture. And here, this average is also taken for large system size and going to infinity. I should have written it, but I just moved it with the arrow over there. So in statistical physics, in normal equilibrium statistical physics, this measure here in a standard equilibrium statistics, this measure here is given to you by Boltzmann, Gibbs. So which kind of measure you have to use depends on the conditions under which you have set your system. So for example, if you set it to be closed in isolation from any surroundings, then you have the microcanonical measure to use here. If open system with the possibility of having energy exchanges with the environment, with the bath, you have the canonical to be used, and if you have the possibility of also exchanging particles, you have the grand canonical. So this is normal stat physics or stat mech of standard equilibrium condition. And then, any not pathological observable will satisfy the fact that the averages over time that you compute should coincide with the averages over the measure that you use. Now, the thing is that when you have these integrable systems that, as I said, sort of regained interest from the experiments on cold atom systems that people are doing, for those cases, there is no reason to believe that this the standard ergodic hypothesis will apply. So there is no reason to believe that you will have the standard microcanonical for the closed system or the standard canonical for the situations in which you can exchange energy with the surroundings. So what happens? People have asked themselves, what happens with this hypothesis and with this kind of equivalence between averages over time and averages over static distributions for integrable systems? So what are integrable systems in 2 words? you have a normal statistical physics, the kind of problems that you study in statistical physics, when you say that the problem is closed, what you say is that, okay, the number of particles, the number of degrees of freedom is constant, it doesn't change, doesn't fluctuate. You typically say that the volume is also constant, doesn't change. And you also typically say that the energy is conserved. It doesn't change, it doesn't fluctuate, it's not, no, the total energy of your problem is conserved. So for example, if you have a system of particles, then you have kinetic plus potential energy, which is conserved. You can have a few other constants of motion. You can have, I don't know, total momentum in certain cases, but only a few in the cases you're used to studying. Now, in integrable systems, what is special about them is that there are n constants of motion. And n is the same n that I wrote here, is the number of degrees of freedom that you have in your system. So you have a lot of constants of motion. You have a macroscopic number of constants of motion that reduce a lot the size, if you wish, of the phase space. I write this as the phase space. It's a drawing of all the possible values of the x's and the p's. In a normal situation, once you have chosen the initial conditions, well, you have chosen a subspace of this complete phase space where, the energy, the volume, and the n are fixed. This is the case, the standard case. But now you don't have just this very few number of constants, but you have n of them. So this has been reduced a lot. You do a little drawing like this. Just a little. They have many constraints that make, the available phase space for your dynamics very reduced. So people have asked the question, what happens if I let my system evolve, one of these integrable systems evolve from some initial condition, I let it evolve, I compute averages over time, just like here, and then I wonder, what do I have to use for the measure over there? Do I have to use, if my system is completely isolated from the rest, a microcanonical measure in which I fix all the constants of motion to have the values determined by the initial conditions? And then my evolution explores the available phase space in a flat manner, like in usual microcanonical distribution, but just, restricted to this little black region here. In the classical mechanics, this is true, this can be proven, and I can give you some references later on if you wish. So in classical mechanics, it is true that a dynamics like that, the Newtonian dynamics with n constants of motion, will explore this great dashed region uniformly, and I can use a microcanonical measure where I fix all the constants of motion to have the values of the initial conditions that they take at the initial conditions. But as you know, in statistical physics, it's hard to make calculations in the microcanonical setting, right? We always like to do calculations in the canonical setting because it's much easier. So then people have asked, is it possible to go from the microcanonical description, which, except it is true, it holds for integrable problems, is it possible to go from the microcanonical to the canonical? Is it possible to make the step where one says, say that I'm interested in some portion of my system, in real space, real space portion, part of it, and consider the rest as a buff with respect to the portion that I selected. So now I make a drawing of, this is my real system in real space. So in statistical physics, one is usually used to say, okay, if I want to focus on this part of my system, I can consider the rest as above with respect to this one. And then I can go from the microcanonical description of the full system in real space to a canonical description of this piece over here. So in standard equilibrium, one goes from the raw microcanonical, which is flat on the constant energy surface of phase space, to the canonical description where you have energy on top, you have inverse temperature in the Boltzmann factor, and okay, Z is the partition function, which is the normalization. So this description represents what's going on in a portion of your system on which you are interested in, and represents, whatever the observables are going to do if you confine yourself to measuring in this selected part. Now the issue is, if I start from a microcanonical description of the integrable problem in this very selected piece of my phase space, can one do also this jump and go to something that generalizes this canonical distribution? And the guess for the generalization of this canonical distribution that people have proposed in the context of quantum systems, and they have checked it in certain cases, is that the generalization of this is going to be something of this form. So you see, in the place of the exponential of E minus beta E, the total energy, the only global constant of motion in the normal case, here, what you have is a sum over n objects, which are these n constants of motion. Where did I write it? Here. The n constants of motion that I'm calling I mu. Mu, again, goes from 1 to n. And these I mu's are functions of the variables in your system. So here you have only one, and E in a normal case would be something like kinetic energy plus potential energy. Right? In the standard case, this is the E that goes here, and you have only one. Well, here you have n objects to put in the exponential, and you have n like generalizations of the inverse temperature that I'm calling gamma mu. And here the I mu's are these I mu's here that depend on all the positions and momenta of the particles. Yes. No, exactly. No, I'm assuming that the full system is integrable. The full system is integrable, but next in the model I will show you, well, you will see how it goes in a model that is completely solved. Yeah. Okay, so this is, as I said, the guess that people in the quantum context with where everything has to be generalized to Hertz and operators and so on and so forth, have put forward. This is called generalized Gibbs ensemble, and it's the measure with which is easier to make calculations than to work with some microcanonical description. The problem is that in many cases, it's not easy to identify which are these constants of motion, which are the operators in the quantum problem that you have to put up here. And okay, there has been a lot of discussion around this problem in the literature. And in certain cases, as I said, it was ascribed to the quantum nature of the problem the people were studying, certain properties that they were finding. So what we tried to do, like 5 years ago, more or less, we started looking at this problem from the classical point of view, with a number of collaborators that I'm going to mention in a second. So just to finish the discussion about the ergodicity, once you assume, or what you want to really check, is whether this measure that appears here is the one that is going to ensure the equivalence between time averages and statistical averages, where here you compute this statistical average over this GGE measure. Okay. So this is the question that we will try to answer, or it will give you some that we tried to answer in a problem which is completely solvable, but it's not completely trivial, because it's what people in the context of integrability call an integrable system in interaction. I will tell you what it means by that in a sec. So this I can erase now. So now the aim of the second half of my talk is to exhibit a model which is completely solvable and that is very old. It's in the literature since this year. It's due to Neumann, the one of the boundary conditions. And it's basically one of these integrable systems that can be studied in full generality, that people in the context of integrability have studied for a number of degrees of freedom n finite and small. But we want to study it in the limit of n going to infinity first, and consider long times eventually, but after n going to infinity, in the same way as I was writing on the blackboard. And before I forget, let me mention the collaborators with which I looked at this problem. So these are, oh, sorry, I was going to write Messi, but it's Messi. From Argentina. And Barbier. This is my collaborators in this project. So the model is the model of a particle that is confined to move on a sphere. So the position of the particle on this sphere I can draw with a vector that points from the center to the sphere. So this is the position of the particle. Let me call it S. A strange name for a position, but the reason why we call it S is because this problem can be mapped on a spin glass problem. And I won't say much about that because I will not have time, but just to tell you that this is the origin of this strange name for a position. So this is a position. And then the sphere, I will choose to have radius square root of n. So this means that s squared is equal to n. And there is also a velocity or a momentum that the sphere has. And the dimension of the sphere, the dimension of the space with where this system is moving is going to be n. So the S vector has n components, right? So n is equal to 3 in my drawing on the blackboard, but I'm going to consider generalizations in which n is not 3, but it's 4 or 5, n going to infinity. Right? Okay, so I have the motion of a classical particle on the sphere, and I will also add some potential energy. So for the moment, I only have for the total energy, kinetic energy, so 1 over 2m, sum over mu, going from to n, mu squared. And now we will add some potential energy. And the potential energy that I will add, I will make it quadratic. So mu are the coordinates in this space, mu1, mu2, mu_n. P mu is the component of the P vector. The nth component of the P vector, according to this Cartesian system of coordinates. S mu are the coordinates of the position, and lambda mu are like spring constants. So what this means is that there is a quadratic potential in each of the directions of this space, and the lambda mu's are all different. Let's take them all different. And for the kind of model, for the realization we looked at with my colleagues over there, because it's convenient to do calculations, and because also makes the connection with the spin glass problem more direct, we took these lambda mu's to have a special set of values. Okay, but this is not necessary. So we chose the lambda mu's. The lambda mu's are fixed. And I can tell you more about the kind of choice of the lambda mu's that we made. They're positive and negative. It's not necessary for all of them to be positive. You see there is a minus sign. Okay, this is the convention we use. There are as many positive as negative. And there is no problem of stability of this problem because of the spherical constraints. So the particle cannot, fly away to infinity. It's constrained to be on the sphere. So there is this energy plus the constraint to be on the sphere during the motion. So this is the model that Neumann studied for n equals 2, 3. And then other people looked at this later on for larger values of n, but always finite and small. Now, this problem is integrable because there are these expressions so these expressions here, one can show rather easily that under Newtonian dynamics, are conserved. So what this means is that the time derivative, which I write here with this dot, of all these I mu's is equal to 0 for all mu's. For all mu. Yeah, so this is, if we use Newton dynamics, and this is what we want to use. And you see that there are n of them. This is for every n. For every mu. So this problem has n constants of motion. So it's integrable in the way I defined it to be integrable. Now, as I said, I mean, people looked at this problem for finite n. We want to look at it for n going to infinity. So it seems to be, lost cause to look at this, solve this problem for n going to infinity. But it's not. There are different methods that we can exploit that allow us to study the dynamics of this problem, and that allow us to study as well the statics of this problem as characterized by this measure of GGE kind. So let me tell you more about the kind of procedure that we use, and a little bit about the kind of techniques that we use to solve it, and conclude with some comments on what we find. So first thing is, what do we want to do? We want to choose initial conditions evolve them with Newton, choose some observable, relevant observables, here I'm looking at the dynamical evolution, so the time-dependent evolution, so the equivalent of this A, and then compute the average over time, as I said, and then compare to the A average with the GGE. Now, I said that I wanted to take n to infinity. So, here I have a single particle that is moving, but it's moving in a large dimensional space where I take n going to infinity. So this is playing the role, this fact of taking the number of coordinates to infinity is playing the role of taking the number of degrees of freedom to infinity. Because the number of degrees of freedom now are the coordinates and momenta of my single particle. Okay? So the large n limit is ensured by this number of coordinates going to infinity in this same problem, although I'm working with a single particle. It's not a many-body particle problem. It's simpler, but it also makes life easier to deal with this problem. Yes. Yes. Yes, you see, this is like an angular momentum, this thing below the square. This is like an angular momentum operator, if you wish. So the problem is that since you have these harmonic potentials, it's not the normal, just the bare angular momentum, which is conserved, but you have to correct it somehow by the values of these harmonic potentials in the different directions. And this is what is done by this denominator here. So it's like a generalized angular momentum, which is conserved in this problem. And you can recover the total energy from a linear combination of these I mu's. So total energy is conserved, and it's included in these I mu's as a linear combination of them. And the spherical constraint is also satisfied by these I mu's in the sense that if you sum over all the I mu's, you get n as for the Sn squared. So there are two, constraints, let's say, on the I mu's that one can just verify by doing the calculation. It's very easy. So the form of these constants of motion was derived by Karen Uhlenbeck in the 80s. Well, much later than the initial proposition of the problem, but okay, they are in the literature. They were in the literature since 50 years. Roughly. There are other questions from the students, perhaps? Yes. 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 So at the microcanonical level, if you consider this problem completely isolated, from the rest of the world, which is what I do in the global problem, as Herbert was asking. There is still dynamics in the region of phase space that is available, which is not just a single point. Because you see, maybe this can help. So mu goes from 1 to n, but if you look in phase space, you have the x mu's and the p mu's. So in phase space, you have 2n. So you still have space to move in the region of phase space, which is restricted by the conservation of these quantities. You still can have non-trivial dynamics there. You still do have. Yes. Yes. The constraints do commute with each other. They do. Yeah, so here the equivalent would be Poisson brackets. The Poisson brackets is 0 if you do the calculation. Yeah, yeah. Other questions here? Yes. Yes. Help? No. So you see the constant, well, for example, something I will do, which is I will do a sharp quench to have a non-trivial dynamics. So the sharp quench I will do in changing the lambdas, because you see the energy, which are the parameters I have? I have these lambdas, or I have the mass. I could change the mass, or I could change the lambdas. I am choosing to change the lambda. So in the simplest setting of the non-trivial dynamics that we looked at, we change them sharply. So you change them sharply. Once you change them, and you choose the final values of the lambdas, you fix the values of the I mu. And then they are kept forever. If you change your lambdas gradually, you will be changing your I mu's gradually as well. So, but we didn't look at that problem. That would be another procedure. Okay, so which is the kind of dynamical procedure that we chose? So, as I said, choose initial conditions. So this means we have to choose the set of x mu at time 0, p mu at time 0, to be on the sphere. But this can be done. So it turns out to be, I can give you more details. It would be a little bit technical to explain it in the rest of the talk, but there are basically two nice families of initial conditions that one can choose and that behave very differently along the dynamics. One corresponds to taking a point roughly anywhere on this sphere. We call them delocalized because there is some interpretation to this word. Okay, it doesn't matter. Anywhere on the sphere, you put your point and you start it with a velocity that satisfies the spherical constraint, so that, keeps the particle on the sphere. And then there is another direction which is special. Let me tell you that it's this one. That just corresponds to the maximum value of the lambda. Doesn't matter, you cannot understand it from what I'm saying, but let me tell you that just this, that there are two kinds of initial conditions which will behave differently along the dynamics. But for any of these two choices, one can do the Newtonian dynamics. So how do we do the Newtonian dynamics? You either do, there are two methods. You either do just solve Newton equations one by one. There are efficient numerical methods to do it. You have to go through some numerics here. I mean, a lot of numerics. It's mostly numerical, apart from some tricks. But there is another method, which is the one that I will tell you about tomorrow in my first lecture, which is going to be an introductory lecture as well, which sometimes is called dynamic mean field theory. And basically what this does is that instead of looking at mode by mode, it looks at the evolution of these quantities So this is like a self-correlation function of the position of the particle at two different times, average over the initial conditions, and it depends on two times, at which I look at the configuration first, and then I look at the configuration later on, and I correlate. So it's like looking at this arrow and this other arrow, and correlate the two. You make the overlap, you make the scalar product between this vector and this other vector. So there is a way to write integral differential equations that I will show you tomorrow for this correlation and for a companion object, which is a linear response function. Again, this average over initial conditions under the field. So one can write down equations that control the dynamics of these two objects, has information about the choice of the initial conditions, and has information about which is the evolution that you're going to do. So which are the lambda mu's, which are the lambda mu's that you're going to choose in the Hamiltonian that rules the dynamic evolution. So I don't have time to go through these details. These equations, dynamic mean field theory, or another technical word is Schwinger-Dyson equations, these can be solved analytically. So you have access to the evolution in time of this x mu of t, p mu of t, from this method here, and you have access to this time dependence of the correlations and linear responses from this other method. And combining the two, you can compute quantities like, for example, S mu squared of time, average over the initial conditions, average over time, or P mu squared of time, average over the initial condition, and over time. So the time part of my ergodic hypothesis test that I want to apply. And look at this, I can compute for each mu. Result in the modes, in the directions, in the coordinates, I can compute this one from this technique. But now, I want to compare to the averages of these same objects with this measure. So, first question about this measure, what is gamma? What are the gammas that I have to use? So, the gammas that one has to use are fixed by the initial conditions. So let me put it here. I complete my description here. Fixing the gamma mu's. So when I start my dynamics, the I mu's have certain values. So the I mu's have these expressions. I choose my initial conditions. I have chosen the S mu of T0, the P mu of T0. So initially, I know my I mu's. If I want a description with this generalized Gibbs ensemble measure to hold, I will ask that these initial values be equal to the average of the I mu's under the GGE. So this is a requirement. This is similar to fixing temperature in the Boltzmann distribution by asking that the average of the energy is set by the temperature that you choose. So this is a requirement that appears n times, because this should be true for each mu. So there are n requirements here. So like this, we fix the set of gamma mu's. Similar, as I said, to fixing T by requiring that, you are on the energy shell that you want to be in the normal case. So we know the gamma mu's. And now, if you know the gamma mu's, which are fixed by the initial conditions, as I said over there, now what you can do is try to see whether the averages of the S mu's with this measure and the averages of the P mu's with this measure coincide with those. So the next step that you have to take is to compute S mu squared under GGE. So, for example, what does this mean? It means that you have to integrate over all the X mu's. You have to integrate over all the P mu's. S mu squared here, E minus the sum over eta, let's say, gamma eta, I eta. And you could tell me, okay, this is hopeless, you see, because you have here quartic functions of the variables, because here you have an SP to the square. How are you going to compute this average? It looks like a, hopeless task. It turns out that this thing, with the normalization, can be computed analytically using tricks from disordered systems. I mean, tricks that we are all quite used to apply when we come from the disordered system, random matrix-like communities. So this average here and the same for the P mu's can be computed analytically. They will take, complicated form as a function of the gamma mu's, which have been fixed, which depend on the lambda mu's. Nasty analytical expressions, but still, I mean, you can compare this analytical expression here with this analytical expression there, and you will see that it works. Also for the P's. So for this concrete problem, one can do all these calculations, which seem so complicated, because you see, this Hamiltonian here, this energy may look quadratic, but it's not because of the constraint. This part here is like harmonic oscillators, independent harmonic oscillators, but because of the constraint, this is not just independent harmonic oscillators. This makes the problem interacting in the language, let's say, of the integrable people. So this is the integrable model interacting because it's not harmonic oscillators, but still it can be solved both dynamically and statically with this GGE, and one can check that the predictions hold in the sense that there is ergodicity with respect to this canonical distribution for the selected variables. So you see, each mu I'm picking as the subsystem on which I focus. The rest of the system is like the bar on top of it. And then I can use canonical description, but of a generalized kind. And the coincidence with the dynamical averages applies, holds. Okay, so just to conclude, this is a field of research that has been very active in the quantum realm. So people have been looking at quantum spin chains, for example. There are many which are integrable and can be solved in different ways, and checked these generalized Gibbs ensemble hypothesis. But in the quantum realm, if you wish, many of the problems which have been treated are non-integrable because their steps can be mapped onto either free fermions, free bosons. So in the end, there are no interactions. This is one family. And then the fact that this GGE applies for them is a little bit trivial. There is another set of models that people have been treated, which are interacting in the quantum realm, but the methods to deal with them are quite complicated. I mean, you have to be an expert of these kind of methods to follow them. And again, checks of GGEs have been exhibited in that context. But then there was some, knowledge in the air of the special features of quantum mechanics. And we, as I said, I mean, our aim was to show, okay, no, this is not the special of quantum mechanics, it's a special of integrability. And we can find a model which is very nice and, have a lot of nice tricks to solve it in different ways, where you can show this equivalence of ergodicity or this validity of ergodicity within this generalized GGE. So, and thank you for your attention. I'm willing to answer questions if you have any. Thank you.
And by the way, I think many research students may have a kind of in the rules and existing knowledge so much for a number of things, right?
10. It's not easy. There is no...
Is there a guiding principle or just by guess?
I think it's case by case. Yeah. Actually, in the context of the quantum problems, people have known for certain problems a number of integrals of motion, the equivalent of the eyes, and then they have noticed that they have missed some. So, it's tricky. Yeah, it's not easy. Yes.
You solve this equation through writing down the correlation function and the response function. So the one question is whether the solutions are unique. Maybe you have class-C dynamics and things.
Yeah, that's a good question, actually. For this problem here, one can prove that the solutions are unique. Because the equations that one writes are causal. Because, okay, you start from initial conditions and you evolve in time, and, as theoretical physicists, we can convince ourselves that the equations are causal. Maybe mathematicians, don't accept, but anyway. And then, you can build your solution step by step in time, and then, you are safe that the solutions are unique. So for the dynamics, yes, the solutions are unique. Yeah, tomorrow you asked me to give a kind of introductory talk, so I will give an introductory talk about the equations that rule the evolution of these quantities. This is not unique to this particular problem. It's applicable to any kind of dynamics, basically. You can have Langevin dynamics, you can have dynamics that violates action-reaction principle. And in many of these problems, where you have some kind of mean field-like features behind, which is the case of this one because of this n going to infinity, and the other problems in the context of neural networks, or in the context of glassy problems in their mean field description. You can write equations that close on these two-time objects, and you don't need to go to higher correlation functions, higher order correlation functions, and so on. So you end up with these Schwinger-Dyson equations, which always have the same structure. And then it can be more difficult or more easier to solve them. But the structure is roughly the same. The global structure is the same. There are some details we change. You can make them quantum, you can make them classical. Yeah. So I will talk about that tomorrow. Yes.
Function. You mentioned a trick.
Yes.
And I heard that it may be replica. Is it?
No, it's not replicas. No, but there are tricks which you also use in the replica treatment. basically what you do is, this is quartic, so you can say, okay, it's horrible, but then you do these Gaussian decouplings or Haber-Stratonovich transformations. Different fields are called different ways. So you go to quadratic things, and then you can guess that there is an ansatz that you can make for the dependence of these S mu's and P mu's on average on the parameters gamma, basically. And in the end, you end up with an equation, can show you the details, that it's very similar to the equation that people deal with in random matrix theory to find the Wigner-Dyson distribution, only that it's more complicated. And then, okay, we had this equation, we didn't know very well what to do with it, but then I talked to people in random matrices, and okay, there were some simple tricks to use to go to the complex plane and whatever, and then you solve them. So in the end, it's just basically Haber-Stratonovich and go into the complex plane. That's it.
Thank you for the talk. In going from integrable system to GGE, I understand that you have to couple it to some bath. Will that lose integrability?
No, I'm not coupling it to the bath. I'm saying that maybe it was the same question that I was asked before. So let me make a sketch. So I have my system, which is this one. I have a system, whatever the system is, with a lot of degrees of freedom, which are the X mu's and the P mu's, all of them. This is my sketch here. And now, the S mu's, sorry, and the P mu's. And then I look at one of them as a S mu. For this degree of freedom, the rest is acting like a bath. Like what you do when you go from microcanonical to canonical. You have a whole system which is isolated from the rest of the world and for which the energy is conserved. Right? Then you look at the piece. For this piece, the energy is no longer conserved because it's in contact with the rest. For this piece here, the energy fluctuates. But the rest is acting like a bath on it. Here is the same. I have my whole system, which is this integrable big object. And then when I look at the statistical and dynamical properties of one of these coordinates, the rest is acting like a bath on this one. And for this one, this is the good measure. This measure describes, the long-term properties of this one. And the same for all of them. This is what's going on. It's non-trivial that it will work this way. It's highly non-trivial. But in this problem, it does. One can check it by doing the calculations.
Thank you.
Yeah.
All the quantities, conserved quantities are all fine, but if I look a little bit closer, then the conservation break a little bit because you isolate one out of the others, and then that gives the dynamics to the ergodic.
I mean, maybe I can answer this way. I don't know if it's going to be satisfying as an answer, but look at the I mu. It depends on the full system. Each of the I mu's mixes everything, because here I have a sum over all the mu's which are not mu. So the I mu's are non-local in the sense that they depend on variables of the full system. So maybe what you are having in mind is that I cannot define a constant of motion that belongs to a single mode, a single coordinate. The constants of motion are of the full system.
Yeah,
this is what you meant. Yeah. Okay. Yes. In the same way as here, the energy is conserved by the full system, but if you look at the piece, there are fluctuations. So yes.
Sorry, I just want to have a clarification. Energy equates is there coupling between different degree of freedom?
No. Here, each of the coordinates has its own harmonic potential, and there is no coupling between the mu's. But the coupling between the mu's comes here.
Okay, I see.
In the constraint. So if I can write the constraint, one way of writing the constraint is by, for example, as you're used to, add a Lagrange multiplier. Oh, sorry, this is the one that doesn't work. Okay, so this is the constraint that you want to impose. And this is a Lagrange multiplier. That imposes it. Okay, now this Z here, I have to fix it. So there is a little calculation that shows that the form that the Z has to take to ensure that this that this constraint is satisfied is that Z is, now there is a factor of 2, which I don't remember. So I put proportional K minus V. So this is kinetic energy, and this is potential energy. So in other terms, it's so you have to think that this Z here is equal to this. This is the form that ensures the spherical constraint. It's not obvious to see. I can show it to you later on if you wish. So you see that if I replace Z by this expression here, I see that this term is quartic in the variables. So then this is the one that is making the problem interacting, no? In the sense that it's not just quadratic action or energy, but it's quartic, so it's non-trivial. This is the part that makes the everything non-trivial, the dynamics and the static properties non-trivial. If this line were not there, it could be just independent harmonic oscillators, and a bit stupid as a problem. But with this one, it makes it non-trivial.
Thanks.
Yes. Yeah. Yes. Yeah. No, people have used this maximal entropy arguments to justify this form, or just say, it's a natural generalization in a problem in which I have many constants of motion of the one that I know of Boltzmann kind for the one in which I just have the energy.
So can it be derived in some more fundamental manner than dimensional?
I mean, I don't know of any, more fundamental way of deriving it. For example, you know that the canonical can be derived from the microcanonical by saying, okay, I have my system, I have this decoupling, no, or this, separation of. So one way which is very nice, and it's explained, for example, in lecture notes by David Mukamel, but okay, it's older than that. It's, well, one way where it's well written is lecture notes of David Mukamel in Les Souches, in the School of Long-Range Interacting Systems, but it's not his original. I mean, the other people did it before. But the thing is that you can say, okay, the total energy of my whole system over there is the energy of a system of interest what I'm going to call the bath, which is this, all the rest, plus interaction between the two. And then you start from microcanonical. You say that this thing is conserved. This is cool. You say that the system of interest is going to be much smaller than the bath. You say that the interaction occurs through the interface between the two. So basically you drop the interaction, you make them independent, you make some assumption about the bath, and then you end up with e to the minus beta e, because beta comes from the entropy of the bath. But to do this, you have to drop the interaction between the system and the bath. You have to consider that your system is much smaller than the bath. There are a number of assumptions that he describes very clearly. Now, if you have n objects and you want to apply this kind of reasoning to n objects, then it's a bit more tricky because, you have to say, it's not so easy to separate the orders of magnitude of what's the interface, what's the bath. In this problem here, I cannot really, I erased the form of the eyes, but, they were all mixed, those eyes. So the energy of the eyes is not a sum of local terms like in the energy normally is when you do an assumption of saying, okay, the energy of interaction is only concentrated on the interface between your system and interest and the bath. You are making an assumption of locality. Here there is no locality in this problem, so it's not obvious. So the normal derivations of canonical from microcanonical, you cannot extend them so easily in these cases. So it's more like you make a proposition, and then case by case you will check whether it holds or it doesn't. Yes. No, we can discuss later.
So the density is only valid in the limit of n goes to infinity.
Yes.
So, but practically, how big it should be?
Okay, so in this problem, when we did this numerical solution that I told you, mode by mode, where we need to, do it numerically, and for n equals 1,000, more or less, that we could do as a maximum number, it was okay. It was already enough. And for n equals 100, which was a little bit small, one would say, it was not that bad. So I can show you numerical data. I didn't have time to do it, but for already n 100, it's quite okay. Yeah.
Okay. Thank you.